Hello, good evening. My name is Hunter, and this is content review for general chemistry students. This is chapter 9. We're covering the ideal gas laws and a few extras today. That's my puppy. That's Goose. Hi, sweet baby. Yeah. It's important to take a moment and just enjoy the cute things in life every once in a while. It's rainy. Take care of yourself. Grab a cup of tea, whatever feels good. If you are here live, thank you for joining us. Feel free to engage with the content as we're going through. And if you are watching this in the future, feel free to speed through it at 2x speed. Make me sound like a chipmunk and pause whenever you need to, rewind, whatever works for you. All right. So relating pressure, volume, amount, and temperature. These are the ideal gas laws. Ideal simply means that we're dealing with idealized conditions. This is different from standard temp and pressure that we dealt with last week. These are conditions not taking into account the size that a gas molecule takes up or the intramolecular forces between them. We will deal with that later. For now, all we're concerned about is the pressure. I'm going to go ahead and annotate this as we're going. The pressure in the chamber of gas, the volume that it occupies, N, how many moles of gas are in that chamber, R is the ideal gas constant, and temperature, T is temperature in Kelvin. This is absolute temperature. So where last week we were dealing with differences in temperature where you could switch between Kelvin and Celsius and not worry too much about it, here it's really important that we convert to Kelvin always. So we're going to get some practice at that. So looking at our first problem, number 27, a spray can is used until it is empty except for the propellant gas, which has a pressure of 1,344 torr at 23 degrees Celsius. If the can is thrown into a fire with a temperature of 475 degrees Celsius, what will be the pressure in the hot can? So we're solving for pressure in a hot can, and we're given a few other values. We have a pressure in torr and temperatures in Celsius. So we know we're going to have to do some conversions here. But before we do that, let's again look at these terms that we have and what we're solving for. We have a couple of pressures and we have a couple of temperatures. We can relate these two, and we have a pressure and temperature before and a pressure and temperature after a change. This formula is Amundsen's or Guy-Lussac's law, and it relates pressure and temperature before and after a change. So let's go ahead and fill these in. Our initial temperature is 1344 torr. And because we're not dealing with the ideal gas constant yet, we can leave this in torr. We're just dealing with a ratio, basically. T1 is 273 Kelvin plus 23 degrees Celsius. P2 is what we're solving for. And T2 is 273 plus 475. Gives us 748 Kelvin. And T1 is going to be 296 Kelvin. So looking at our formula again, we're solving for P2. We can simply multiply both sides by T2, which gives us P1 times T2 all over T1. Multiply that out. And we should get a value of 3,396.3. That would be torr. And again, in scientific notation, since we're chemists. A weather balloon contains 8.8 moles of helium at a pressure of 0.992 atmosphere and a temperature of 25 degrees Celsius at ground level. What is the volume of the balloon under these conditions? Under these conditions is always kind of a clue. But this is the first time that we're going to be really digging into this ideal gas equation, which is PV equals nRT, or PIVNERT if you need a mnemonic. We are already given some values. Let's go ahead and highlight those. We have quantity, we have pressure, and we have temperature. We're given R, which is a constant, and that is 0.08206 liters times atmosphere over mole times Kelvin. And this you just need to know. It may or may not be given on your exam. We're given a pressure in atmosphere. Great, don't have to do any conversions there. We're given a quantity of 8.8 moles, and we're given a temperature in 25 Celsius plus 273 Kelvin gives us 298 Kelvin. Now we can solve our problem for volume. We simply divide both sides by pressure to get it to the other side. We have 8.8 moles, the gas constant, 298 Kelvin, all over pressure, multiply that out. Our volume at these conditions is about 217 liters. The ideal gas constant is definitely worth memorizing. Scroll wheel's going a little hard today. Yes, so question in the chat, in order to use that constant, we need to make sure the pressure is in atmosphere. Unlike the previous question, the units didn't matter. That's exactly right. Because we were comparing torr to torr, I think it was, the same could be true if you're comparing kilopascals to kilopascals. Since we're not dealing with any other factors besides pressure and temperature, those relate directly to each other. No conversions were needed there. Because we're working with the ideal gas constant, we had to do that conversion. So good question. Yes. All right. And thanks for chiming in. Question 32. The volume of an automobile airbag was 66.8 liters when inflated at 25 degrees Celsius with 77.8 grams of nitrogen gas. What was the pressure in the bag in kilopascals? So this is kind of what we were just talking about. We're gonna have to do a lot more interconverting between units to make this problem make more sense. But we can still solve it with this PV equals nRT ideal gas equation. So let's first start with what we know we have. We're given a volume. we don't quite have a quantity in moles, but we're given grams, and we know that nitrogen gas is dinitrogen N2. So we will be able to calculate that. We know R, and remember that's liters times atmosphere mole.Kelvin. And I'm repeating these for a reason. The units are important. And if we just memorize the number without the unit and we forget to convert it in later problems, we get into big trouble. Temperature, we had 25 Celsius plus 273, 273.15 if you want to be more precise, but for our purposes, this works. So let's calculate N, the number of moles that we have. We know that nitrogen gas is diatomic. There's two of them. And this should look familiar. The molar mass of nitrogen is 14.01 grams per mole. So we simply double that, gives us 28.02 grams per mole. They gave us 77.8 grams of N2. Do a little dimensional analysis. Per mole of N2, we have 28.02 grams, which gives us 2.78 moles of N2. And with that, we should have everything we need. We're solving for pressure. So we're going to divide both sides by volume to get pressure on the same side, or alone. And let's just start filling out values. We've got 2.78 moles, the gas constant. Temperature was 298. Yes. All over a volume, 66.8 liters, which gives us a pressure of 1.018 atmospheres. We're not done. We need to get to kilopascals. So for every yeah, I'm going to set this up as a dimensional analysis again. So we have so many atmospheres, and per atmosphere, there is 101.325 kilopascals, which gives us approximately 103 kilopascals. And that is our final answer. Jeez. All right. Make sure you can see that. 34. Iodine, I2, is a solid at room temperature, but sublimes, that is, it converts from a solid into a gas when warmed. What is the temperature in a 73.3 milliliter bulb that contains 0.292 grams of iodine vapor at a pressure of 0.462 atmosphere? This one's kind of nice. We don't have to do a lot of converting here. Let's write down what we've got. We're not given temperature. What is the temperature? We're given a pressure in atmospheres. We're given a volume. We are given the gas constant, 8,206. and we need to calculate our quantity. We're given 0.292 grams of iodine gas. Well, iodine solid. Doesn't matter actually. Per mole of diatomic iodine, there are 253.8 grams per mole. Grams cancel out. That gives us 0.00115 moles. So now we can start to solve our problem. We're solving for T, PV equals nRT. We divide both sides by N and R, gives us T equals P times V over NR. We've got our pressure, our volume, quantity was 0.00115, and the gas constant, 8206, should give us 358.9 Kelvin. All right. So this is more of a conceptual problem, and I really like these for lots of reasons. But we're looking at the mathematical relationships between these characteristics, and we can kind of visualize them too. Um, if you think of a massless balloon filled with some ideal gas, if you increase the temperature, those atoms are going to rub against each other, bounce around a lot faster. That's going to create friction. That's going to increase pressure and temperature. Um, and back and forth. Find an example that works for you conceptually. Find some simulations online was actually really helpful for me to really understand these behaviors more intuitively. But I'm gonna drop a graph in here because they're asking us to visualize. Oh, come on now. Shapes, X, Y. One more time. There we go. Okay. So for a given amount of gas, show ideal behavior, draw labeled graphs. The variation of PV. So if we think back, or PV equals RT, pressure and volume by each other equal the rest of this constant. So if we're just at pressure and temperature, pressure is proportionate to volume. Right? To graph that, if pressure is how to explain this? If pressure is high, volume. Sorry, it's easier for me to think about this the other way around. It increases, pressure will decrease. We have PV. Our relationships look something like that. And the variation of volume and temperature. They're on opposite sides of that ideal, so V is directly proportionate. So our graph will look a little bit more. I'll label them. This was inverse V, orange. Variation of, actually, we'll do this the same color. Pressure and temperature are also on opposites of that equation, so directly proportionate. So it's same blue line. And then D, the variation of inverse pressure with volume, is the same as saying volume is proportionate to pressure, and that would chart parallel with that blue line that we drew. My advice is to play around with some simulation to visualize that a little better. Excuse me. All right. Stoichiometry of gaseous substances, mixtures, actants. Calculate the density of Freon at 30 degrees Celsius and 0.9 atmosphere. All right. There's a short, which I'm going to show you here. You can solve it with the equation, but if you know this, it's a little bit more straightforward. Molar mass equals density times the ideal gas constant times temperature all over pressure. Calculating the density of PM over, and we're getting some molar mass free. We can cheat and look at Google, or we can add up the molar masses of each molecule since they gave it to us. And we have 129 grams per mole. We have the gas constant. We have temperature in Celsius, Kelvin, and we have the pressure. So pressure, molar mass, yeah, two, gas constant, temperature. Multiply those out, and you should get density of 4.64 grams per liter. Okay. All right, question 52. The molar mass of a gas, 0.04 grams. What is gas? If 0.0494 of the gas occupies a volume of 0.1 liters at 26 Celsius and a pressure of 37. All right. Same thing. We're given some values. 26 to Kelvin. Pressure in torr. Highlight that. Can't miss it. And we're trying to get to molar mass. We can get to density because we have and a volume. The mass we're given is 0.0494. Density, of course, is mass per volume. So, using that shortcut equation that we just did, we can simply plug in those values to modify that shortcut equation. So now we've got 0.0494 grams times the gas constant times temperature over volume and the pressure torr. From torr to atmosphere, we simply do analysis within the equation now, divide it by 160 to get to atmospheres. It's the same as multiplying by the reciprocal. So we take that monster of an equation. Should get, what should we get? 826. I got 30.01, and that would be grams per mole. Somebody check my math on that. All right. Question 57. A 36-liter gas used for calibration of blood gas in medical laboratories contains 350 grams of CO2, 5 grams of O2, and 4,008 grams of nitrogen 2. At 25, what is the pressure in the cylinder in atmospheres? Besides the ideal gas law formula here, you also need to know that the pressure is the sum of pressures of all of the gas in the chamber. So we're given masses, quantities of each gas. We need to go from masses to moles, and then that would give us the moles that are contained in that, and then we can simply use the ideal gas law to solve. So, some dimensional analysis. 350 grams of 44.01 grams per mole gives us 7.95 moles of CO2, 805 grams oxygen at 32 grams per mole gives us 25.16 moles of O2 and 880 grams of nitrogen. Because these are all diatomic gases, when you look up their atomic masses, make sure that you double them to get the appropriate conversion. We use. This is the total moles of gas in the chamber. So to solve that problem, we have volume, 36 liters. We have the ideal gas constant. We have a temperature of 298 Kelvin. And now we have a number of moles. Would equal 140.84 atmospheres. A sample of carbon monoxide was collected over water at a total pressure of 756 torr, temperature of 18 degrees Celsius, with pressure of monoxide. So we're asked to reference some tabulated, and this is the vapor pressure of ice and water at temperatures at sea level. This is going back to that partial pressure where the sum of all parts equals the total pressure. We're given the total pressure, and the partial pressures of water at various temperatures is well known. So when you have an unknown gas, um, well, we're given a sample of carbon monoxide here and asked to calculate the pressure of carbon monoxide. Um, this allows you to do some cool things like determine the identity of a gas by determining its partial pressure and its mass relative to that of water by bubbling it through a sample of water, which you might get to do in lab if you haven't done it already. So this is a pretty straightforward problem. We're given the partial pressure of water in torr, and that value, sorry, came from right here. So we have temperature, pressure. Yeah, we were given a total pressure of 756 torr. And again, with any conversions, we don't need to. The total pressure equals the partial pressure of water vapor plus the partial pressure of carbon monoxide in the chamber. We're trying to calculate the partial pressure of CO2, carbon monoxide, equals P total minus P. Partial pressure of carbon monoxide equals 756 minus 15.5 equals 740 torr. Keep blocking the question with the chat window. Sorry about that. Joseph Priestley first prepared pure oxygen by heating mercuric oxide, it's HGO, and we're given this balanced equation. Part A, outline the steps necessary to answer the following question. What volume of oxygen at 23 degrees Celsius and 0.975 atmosphere is produced by the decomposition of 5.36 grams of mercury oxide? We've got our gas law. We're given some variables. So first we need to determine the number of moles of mercuric oxide that decomposes. Using the chemical equation, we can then determine the moles of O2 produced by the decomposition of this amount of mercuric oxide. And then from there, we can determine the volume of O2 from the moles of O2, temperature, pressure, etc. So we start with mass to calculate moles and then determine the ratio to moles of oxygen. Answer the question. We're given, what was it, 5.36 grams per mole. There's 216.59 grams. And per mole of oxygen gas, there are 2 moles of mercuric oxide in our balanced equation. So now you have a simple formula that you can punch into your calculator in a single step, you should get moles of O2. And I'm going to go through really quick and just show the dimensional analysis process here. Got grams of mercuric oxide cancels out. We get to moles of mercuric oxide. Those cancel out. We're left with moles of O2. I think that's everything. All right, moving on. Automobile airbags are inflated with nitrogen gas, which is formed by the decomposition of solid sodium azide. The other product is sodium metal. Calculate the volume of nitrogen gas at 27 degrees Celsius and 756 torr formed by the decomposition of 125 grams of sodium azide. So in that previous problem, we had a simple 2-to-1 ratio of oxygen to mercuric oxide, or mercuric oxide. Here we've got 3 to 2. Remember that nitrogen is diatomic. That'll be important later. We've got a temperature. We have an ideal gas constant. We have a pressure in torr. Divide by 760 to get to atmosphere. And we have, do we have a number of moles? We do not have a number of moles. We need to get there. So that's our first step. We are given 125 grams of sodium azide. Looking that up, the molar mass is 65.01 grams per mole. Now we've got our ratio of sodium azide to nitrogen gas. We have, just looking at the, if you can do this in your head, great. If you can't, I'll explain. There are 3 nitrogens in sodium azide and 2 nitrogens in nitrogen gas. Lowest common multiple would be 6, and so 3 to 2. Now we can multiply that out. Gives us 2.884 moles of nitrogen gas. And again, canceling out our units. Okay, now, I apologize, that was not we weren't just solving for moles. We need to go on. We're solving for volume. We've got moles, our gas constant, and temperature all over our pressure equals 71.09 liters. Give me just a second. All right, section 9.4, effusion and diffusion of gases. So effusion is gases moving from chamber to chamber, usually through some kind of orifice. Diffusion is to do with the mixing of gases. A balloon filled with helium gas takes 6 hours to deflate to 50% of its original volume. How long will it take for an identical balloon filled with the same volume of hydrogen gas instead of helium to decrease its volume by 50%? I have written this formula and highlighted it in red for you in advance. Rate A, which A in this case is going to be, I don't remember off the top. This is going to be helium, and B is going to be hydrogen gas. Rate A over rate B equals the molar mass of B over the molar mass of A, all to the half power. So rate A over rate B, we've got the molar mass of helium gas divided by the molar mass of hydrogen gas to the half exponent equals 1.40909 H2 to helium. So if helium, now it's we have a ratio that we can work with now, right? If helium took 6 hours, I'm just going to put helium off to the side here. Yeah, I actually want to write this as a dimensional analysis because I've been writing it that way for all of the others. For every, mm, yeah, no, I'm not going to do that right now. If helium takes 6 hours to get to 50%, and we have this ratio of 1.4 hydrogen to helium, we simply divide it and we get 4.3 hours. If you were on a multiple choice test and you were given these some random quantities, you could intuit, for example, hydrogen gas has a lower mass, it's a little bit smaller, but it's also diatomic. The sanity check here is that this, well, I'm walking this back because I don't want to confuse anyone and I don't want to lead you astray on this. Um, the sanity check here was helium gas, which is smaller, moves out of the balloon faster than the uh, excuse me, hydrogen, which is smaller, moves out of the balloon faster than the helium, which is larger and heavier. Does that make sense? Yes, that makes sense. Okay. A gas of unknown identity diffuses at a rate of 83.3 milliliters per second in a diffusion apparatus in which carbon dioxide diffuses at the rate of 102 milliliters per second. Calculate the molecular mass of the unknown gas. And again, we're going to use the same equation. The difference here is we are trying to solve for MB, the molar mass of B, or the molecular mass, rather. This requires a little algebra. I had to look up what the exponent rules were. If you already knew them, fantastic. But to get rid of this, you simply raise each side of the equation to the reciprocal exponent, which will give us rate A over rate B squared equals MB over MA. Multiply both sides by MA. To get MB on its own. And now we plug in some values. We have carbon dioxide is 44.01 grams per mole. We were given a rate of 102 milliliters per second. And again, let me make sure I've got this right. Yeah, rate A, MA, both are carbon dioxide. And then the unknown diffused at a rate of 83.3 milliliters per second. And all of that squared. Units are going to cancel out. Perfect. Don't have to worry about that. MB equals 65.99 grams per mole. So we were asked to calculate the molecular mass. You can take this a step further and try and figure out what the molecular mass of this, what this is the molecular mass of. Sometimes you can use a tabulated value. Sometimes you can, do some guess and check. The hint here is this molecule has been named earlier in this practice session. I'm not going to name it now. I will maybe in a day or two leave it as a comment on the video on the YouTube channel, just for pride points. Pat yourself on the back if you got it right. So now we're going to look at a few with non-ideal gas behavior. I also see we're coming up on 5 p.m., so I probably will not get through these, but we should do at least one. So 104. A 0.245 liter flask contains 0.467 moles of CO2 at 159 degrees Celsius. Calculate the pressure first using the ideal gas law. We've already done a lot of this. Calculate pressure. Should give us 67.57 atmospheres. So that's part A. Dealing with non-ideal gas behavior, we're now adding in constants or variables rather that account for the space that the molecule occupies and the intermolecular forces between molecules. So attraction and repulsion. And those are accounted for by these variables A and B. And for common substances, those values are tabulated. So I'm going to just pull those into our equation and we'll go from there. I've already done the work of algebraically rearranging the equation here so that it's solving for P, solving for pressure, and I'm just going to plug those values in. So pressure equals, we've got 0.467, our gas constant, and our temperature, all over, we've got volume minus moles times this new variable B. So we've got 2.245 minus 0.467 moles times 0.0427 is our B value, minus the quantity, 3.59 is our A value, times 0.467 squared, divided by 245 squared. I broke this down into 2 steps just to keep it consistent in case I made a mistake in my calculator. I wouldn't have to start all over again. We should get 60.5 atmospheres. Notice that there is a difference of about 7 atmospheres, right? So that is why we have these other formulas that take those into account. C simply states to explain the reasoning for the difference. The A term accounts for the intermolecular attractions between molecules of gas, and the B term accounts for the space that the molecules take up, and that is why we have this difference. Identify which correction, that for pressure or volume, is dominant and why. We have to look at this quantitatively in our equation. The change in pressure is going to have a greater impact. The B term, when pressure is high, the B term dominates since it changes total volume, and the term is in the denominator, which has a much larger effect than if it were in the numerator. Was that the last question? It was. Oh my goodness. All right. We made through it. We made it through in an hour. Thank you for those of you who tuned in. For the rest of you, thanks for stopping by. I'll post the answer to the extra question um, after this video uploads, probably this weekend. And if you have any questions, feel free to reach out. And I will see you all next week.